All right, so in doing this problem, when you do the free body diagram, you don't have to make this artistic picture with an arm and a scale and all this other stuff. You just have to make a line, just like we've done on all these other ones. So if I do this, I'm going to have a line. Oops, let me do it. So this is my free body diagram. The line that I just drew represents the distance from the force on the farthest end to the force on this end. I mean, you can put the fingers, like I don't have to put it right on the end. What's important is what's in between the muscle and the scale. So if I need to know the correct directions for these. Now muscles all contract. So since a muscle contracts, then it's going to pull. So the force from the muscle is going to be in this direction. So what I just drew, this is the muscle's force. It's going to contract and pull in that direction. Well, right next to the muscle is a bone, and that prevents the whole arm from going up when at the elbow joint. So we want this point right there to not move. We want everything to move around it, but we don't want that point to move. So it doesn't move because there's a bone there, so that when this pulls up, that's going to be a force down caused by the upper arm, because it can't go anywhere if there's a bone in the way. So we're going to have right there, we're going to have a force in that direction caused by the upper arm. Now, the arm itself has a weight. If I hold my arm like this, and like as an L, and I relax my arm, it goes down, right? So I hold it here and I relax it, it goes down. So the force from the arm is going to be in that direction. And I know I'm drawing these in different lengths because I know that's 6. I know if I look at the picture, that's 6 pounds, that's 28 pounds. So, and these two, I don't know what they are yet, but I'll tell you, they're going to be pretty big. So just just making this small, because I know that's going to be smaller than these two. Now the scale. The person is pushing down on the scale, so the scale provides an equal and opposite force in the other direction. Remember, we're not looking at the force that's on the scale. We're looking at the force of the scale on the arm. So what direction will that be? Up. So we're going to have an up force somewhere over there. And it doesn't really matter that I have like extra room over here, which would probably be the fingers, because you have it here, probably be the fingers. It doesn't really matter. Sometimes they will give us from one end to the other because based on the different lengths, we need to know like the length of the whole thing. So sometimes that is important. But in this problem, all that matters is from there to there. Those are the only things that are causing this thing to rotate. Now the natural pivot point for the arm is right there. That's the natural pivot point. So it doesn't mean that that's what I'm going to use as my pivot point, but to solve part A, it is going to be what I'm going to use as the pivot point, because if I label these, let's call this M for muscle, and let's call this B for bone. Since it's the bone, the upper arm bone, you call it U, call it E for elbow, whatever you want to call it. These two, we know what those numbers are, so I'm just going to label this 6 pounds, and I'm going to label this 28 pounds. Now I know the arm isn't moving when all of this is happening, because I'm pushing down on the scale, but my arm isn't rotating. So once you have your descriptive equation, the next thing to do is to sum up your torques, and I know that when I add them all up, they should add up to 0, because it's not rotating. So if I'm going to solve for the muscle, look, I don't know what this is and I don't know what that is. So if I want to know this, I make this the pivot point. If I wanted to know this, I would make that the pivot point, because I have 2 unknowns. I can eliminate one by simply making it the pivot point. So the muscle is the muscle making it go clockwise or counterclockwise? Clockwise. So plus or minus? Minus. So this is going to be minus the muscle times its distance to the pivot point. Now, I didn't put them in. Let me put those numbers in. So this distance right here is 6.3 inches. And this distance right here is 5.4 inches. And this little distance, I can't really fit that thing in there, so I'm just going to say that's 0.7 inches. So it's going to be m times 0.7 inches. That takes care of the torque caused by the muscle. Now, what about the upper arm? I mean, what about the weight of the forearm? Is that making it go clockwise or counterclockwise? Counter? Look, that's my pivot point. So if I have it down to the right, it's going to go around like that. So that is going to be another minus, because clockwise is minus. So it's going to be 6 pounds times its distance to the pivot point, which is 5.4 inches. Both of those are negative. So the last one better be positive because it can't be moving. I can't have all torques the same direction because then the arm would be going around. So, but let's check. If I look here, this one is an up force to the right of the pivot point. So that's making it do what? Counterclockwise. So it goes around like that. So that's going to be plus 28 pounds times its distance to the pivot point, which would be what? 11.7. That's where the mistakes are that I see on the test, are those that get the wrong distances to the pivot point. Usually people are going to multiply a force by a distance. But if you get it wrong because you don't have the right distance. Yes? This? Because the muscle here contracts. When a muscle contracts, it pulls. So it's pulling in that direction. It's like, look, you got two arms, you got two muscles in your arm with your elbow joint. You've got the tricep muscle behind it, you got the bicep muscle in front. So the bicep muscle, when it contracts, makes your arm go in that direction. When the tricep muscle, which is behind, it makes it go in that direction. All right, so it's making the arm go in that direction, which is the clockwise direction. Okay, so if you solve this for m, so basically I would just, if I move this to the other side, let me just solve it for m. So m, I'm going to move this term to the other side, which is this side now, and then I'm going to have that divided by this. So it's going to be 6 pounds times 5.4 inches plus 28 pounds times 11.7 inches divided by 0.7 inches. Now the negative, I move this to the other side. I move this term to the other side and left this stuff here and then divided by 0.7. I know I have it on this side, but it was moved to the other side and then I divided by 0.7. So solving that, and you get this one. Yeah, you're right. So this one, that's negative. So yeah, so negative 6 pounds times 5.4 plus 28 times 11.7 divided by that. And the answer came out to be 422 pounds. Is that it? So I know that this thing right here is 422 pounds. Now, if you're in a rush and you don't want to do the same thing to solve for the other one, which sometimes I would suggest you do, because if you do it the same way and everything works out, it's a good way to check. But let's say if you're in a rush, well, I know that the forces up have to equal the forces down. So if I add these two numbers together, they add up to 450 pounds. So if that's 450 pounds, then these two have to add up to 450 pounds, meaning that number has to be what? If these two are 450 and those have to be 450, then what does that have to be? 444. So 444 will be the answer for the other one. Now you can do it that way, just summing up your forces, or you can just do it this way. We just solved for that. What I would do for the next part is I would just move my pivot point from there to there and then do the same thing I did down here.